Hello student to the Foundation of Classical Electrodynamics course. So today we have lecture number 12 and today we will make a small recap of gradient, divergence and curl operator and the related theories that we have developed in last few classes, and also like to prove few important vector identities. So let us start the class. So today we have class number 12. So, as I mentioned, today I will have a recap. So, the first thing we should mention that this is del operator. We define this del operator in Cartesian coordinate system in this way. This is a vector operator and it is defined in this way. Okay, and this is a vector operator. Now, the next thing, how to operate these things over some function. So, we mentioned that t, which is a function of x, y, z, it is a scalar field. Now, I can operate these things over that. This operator is operating over this t x y z and give rise to something like I del t del x plus j del t del y plus k del t del z. Okay, it will operate and give us this. Now, this quantity is a vector quantity. And what does it mean? What is meaning of that thing? So, these things eventually tells us that this is the direction basically. This is points in the direction of maximum increment of the scalar field t. So, t is a scalar field which is changing over x y z, and I am putting this operator over that scalar field. So, that basically gives us the direction along which it is changing in the maximum way. Now, the next important thing is this quantity is eventually this. and these things I can write as d of t, that is all. If I write this gradient of t dot dr in this form, then the next thing I can write is, if I want to calculate, do the integral, line integral, because it is essentially give us a line integral where gradient of t dot dr. So, this is a line integral. So, that eventually means that I am making a line integral of this thing dt, which gives me simple result Ta Tb minus Ta. So, that is path independent. Now, after writing this, we can extend the idea and make a closed line integral for the same quantity, and when I write a closed line integral, it should give me simply 0. That is a very important information that we should note. Okay. So, that is whatever we have learned about. This is the gist of this del operator and how it operates over a scalar field, and what is the working principle and working mechanism, everything is shown here. Now, the next thing I mentioned that what is the form of this operator in other coordinate system. So, at rho phi z, you can see the operator looks different, unlike the scalar, unlike the Cartesian coordinate, it is showing something like this. This is the form of this vector, form of this vector operator over in as a function of in cylindrical coordinate system. What about the spherical coordinate system? In spherical coordinate system, I should write it r, then theta, and then phi, and the operator reads like this, then theta 1 by r del del theta plus phi, then r sin theta, and this. We derived this, how one can transform from this to this. This is the original Cartesian coordinate, and from Cartesian coordinate I derived in few class ago that how to convert these things to here. In the same way, you can convert that by using the relationship between x, y, z and r theta phi. You can derive that it is coming like this. Later we will see that for curvilinear coordinate system we can generalize this and try to understand that how should be the general expression. Okay. After that, the next thing we learn is, this is 1 okay, and this is 2. That is the divergence of a vector field. And what was that? How it operates? The operator del is same, but now the operation mechanism is like I am working a dot product kind of things. And what is the outcome here? The outcome is del Ax del x plus del Ay and this quantity is a scalar quantity. Where A is having a component, A is a vector field, should have a component like this. Okay. The next thing is what it measures, what is the meaning of these things. If I have a quantity like this, what is the physical meaning of that? We will also explain this stuff. So, it basically measures how much the vector field A spreads out from a given point. So, with this divergence we basically find out that for a given point how this vector field is spreading out, how much. The next very important thing we learn, very important theorem we learn, and that is the divergence theorem. This divergence theorem, the statement of this theorem is like that: if I have a volume integral of the divergence of A, then that value is the total flux over the surface that is enclosing the entire volume. So, this surface is enclosing the entire volume. So, I am calculating a volume integral here. So, that means I should have a volume. So, this surface should be such that it is enclosing the entire volume, then this identity holds. Well, what is the physical meaning? The physical meaning that this is the total flux. So, total flux is same as divergence over volume. Total flux is divergence over volume. Okay. The next thing we mention is also having some significance, and that is 3 is called Laplacian operator. What was Laplacian operator? The Laplacian operator was something like this. This is a scalar operator and it defines like a second order partial derivative of x, y and z, which like sum over. Okay. And how it one can consider these things as a, first I am having a scalar function and first make the gradient of the scalar function phi, and you are getting a vector, and then if you make a divergence of that thing, so what you are getting is simply the Laplacian of that function. Okay. So, first you are making the gradient and then you are getting a vector quantity. That vector quantity, if you want to find out how diverge it is, so you are now making a divergence and you are getting this, and this simply gives us this stuff. Okay. And also this operator can operate over a vector field, that is very interesting. So, this sorry. So, this operator can operate over a vector field, and we can have the form the right hand side like this. So, this is a scalar operator, so it can operate over a scalar field as well as on a vector field. This is the way one can define. Okay. So, the next thing we discussed was, this is the third point, fourth point rather, that the curl of a vector field. The curl of a vector field. So, how I calculate the curl of a vector field? So, this is my operator. Now, instead of having divergence, I am taking curl, that means I am making a cross product which results this. Shorthand notation of partial derivative and then x a y a z bracket close. So, this mind it, this is a vector quantity, and component wise if I want to find out what is this. So, the ith component of this is simply epsilon I j k del a k del x j. So, that is the way we can define. So, x component, if I want to find out what is the x component, is simply give us this. Also, there is a very important theorem that is associated with this curl stuff, and that is the Stokes theorem. What is the statement of the Stokes theorem? The Stokes theorem tells us, if I have a curl and then from this curl, if I calculate the surface integration of a given surface, whatever the result I get, that should be identical with this quantity where we calculate the closed line integral, and this closed line is encircling this surface. Okay. So, that was the statement. And what is the physical meaning? I must mention that also. What is the physical meaning of these things? What it measures? It basically measures the curliness or twist of the vector field A at some given point. So, this is all over the recap in last couple of classes whatever we have done. So, I make it in a single class, so that you can appreciate that how del operator is there and how it operates over the scalar field, giving a something called the gradient, and then how you calculate the divergence for a given vector field, and what is the meaning of divergence, what is the important theorem related to divergence, which is the Gauss's theorem or divergence theorem, which tells us that if you calculate the volume integral for a divergence, that should be identical to the surface integral, closed surface integral, and the surface should be such that it is enclosing the entire volume over which you are calculating the volume integral. Then the Laplacian operator is a very important operator. In later part of the course, this operator will come very frequently. Then curl of a vector field, how you can calculate the twist nature of a vector. A vector field is a field that is evolving over the space, and for a given point, if you want to find out how curly it is, how twisted it is, then you can calculate this curl, and if it is a non-zero value, that means this vector field is twisted there. Okay. And then the Stokes theorem suggests that if you calculate the curl and then make a surface integral, then that value should be identical if you have the vector field and calculate the line integral, but the line should be such that it is encircling the given surface over which you are doing the surface integral. So, this is overall the recap I wanted to do quickly today. Now, the next part of the class, I will going to prove some vector, very important vector identity, and that you should be very careful of. Okay, so the first vector identity I like to show is this. So, I want to calculate the curl of a gradient of some vector. What should be the value? So, I know this is a vector quantity, this is a vector quantity, the gradient which is giving us the direction. Now, if I want to find out the curl of that thing, you will see this is identically 0, always you will going to get 0. So, how you prove that? What is the proof? That I am going to do here quickly by using these symbols, useful Levi-Civita symbols that we know. So, let us try to find out first the ith element of this vector, because at the end of the day this gives us a vector quantity, right. So, the ith component, if I want to find, so how you write it in terms of epsilon? It is epsilon I j k and then del j, and whatever we have here, the kth component I should write. Okay. That is the way, and this is the derivative with respect to this j. So, here then further I can write it epsilon I j k, these things, and these things, what is phi and what is the kth component of the phi? It is simply del phi del k, right, simply that. So, the kth component is k is 1 2 3. So, that means x y z. So, the x component is del phi del x, y component is del phi del y, z component is del phi del z. So, instead of writing x y z, if I write k, it should be del phi del k. So, then it is del k phi that we are having. Okay. So, now what I do is here how many indices are there? You can see that there j k and j k are repeated index. I am writing in an Einstein notation. So, if these two are repeated index, then if I expand this, so one thing is I j k del j del k phi, that is one, and another thing I should write, and that thing is another option is I k j and then phi k del j phi. Okay. Now, we know that epsilon I j k, it is 1, but epsilon I k j is equal to minus 1. So, this we know. So, we can write in the next line that this is epsilon I j k. Okay, I do not need to write because I am now putting the value. So, epsilon I j k is not required anymore because I am going to put this value. So, this is eventually del j del k phi, and here we have a minus sign because this is minus 1, del k del j phi. Okay. Now, you can see that this operator, what is the meaning of del j del k? This means I am having the operator in this form. If j is x and k is y, so it is eventually del 2 del x del y, but I know that this is also equivalent to del 2 del y del x. So, these things are same. So, since these and these are same, this operator over phi and this operator over phi is same. So, I can have simply this equal to 0 as del j del k is equal to del k del j. I am making the partial operation, but I have changed the order, but even if I change the order, then it is commutative. So, at the end of the day we will get the same result, and this gives us 0. So, that means we always have, this is in general. So, we should note that we always have the curl of a gradient of a scalar field to be 0. This is a vector identity, it is identically 0 without any condition. For all the cases, this is 0. So, that is the first identity I like to prove. Now, the second one, second identity. The second identity is, if I want to find out the gradient of a curl of a vector field, then what should I get in the right hand side? So, I find a curl first. So, divergence of a curl of a vector. So, this is a vector, it gives rise to a vector field. Now, I try to find out what should be the divergence of this quantity, and again you can see that this is identically 0, always we will get this is 0. How to prove that? Okay. So, let us start with the expression. So, the expression is saying that divergence I need to calculate, and this is curl. So, this quantity, if I write, I should write is del I and del I and curl of A and I, because this is a divergence operator, this is a divergence operator, both the cases it should be I. Now, I expand this del I, how I expand this ith component, because we know that curl, this is epsilon I ith component is epsilon I j k del j a k. So, that I am going to use epsilon I j k del j a k. So, this I can write this epsilon I j k del I del j a k. Okay. And now, I will play with that. You can see that how many dummy indices here I j k, this is a repeated. So, that many combinations you can have. So, now you need to start putting the value. So, the first value should be say 1 2 3, then del 1 del 2, then A 3 plus epsilon 1 3 2, then del 1 del 3 A 2, then plus epsilon 2 1 3 del 2 del 1 A 3 plus epsilon 2 3 1, then del 2 del 3 A 1, and finally, we have epsilon 3 1 2, and then del 3 del 3 1 2 del 3 del 1 A 2 plus epsilon 3 2 1 del 3 del 2 1. So, for each value you have a value with the negative, and if you calculate you will find this is identically 0 for each. For example, epsilon 1 2 3 is here and epsilon 3 2 1 is here, and epsilon 1 2 3 is there, epsilon 2 1 3 is there. So, these two will cancel out because these are the negative of this one. In a similar way, 1 2 3 A 2 is here, then 3 2 1 A 2 is there. So, these two will going to cancel out. So, I am just showing that these things will cancel out with this one, these things will cancel out with this one, and these things will cancel out with this one. So, give rise to a 0 value. Okay. Finally, this is my last today's last identity that I am going to prove, but very important identity. This is the third identity I am going to prove, and it is saying that what is the value curl cross A. I need to prove that, and the result first let me write. It is a very famous identity, and you should remember this identity, because this will going to help us a lot in future, and this is the identity. I am just blindly writing, I will prove that later. So, this is curl vector quantity, and I will then calculate the curl over that. So, at the end of the day, whatever I am getting is a vector quantity. Right hand side, what I am getting, this is a scalar quantity, but I am taking the gradient of that thing. So, this should be a vector, and this is the Laplacian operator operating on a vector field. So, that should also give you the vector. So, right hand side and left hand side both will give us the vector quantity. So, that means at least this is fine. Now, I am going to prove this stuff quickly. So, curl of a ith component, if I calculate, then it should be simply epsilon I j k and then del j and the kth component of this quantity, right, kth component of this quantity. If I elaborate, it should be epsilon I j k del j. This quantity is how much? Del j, sorry, this quantity is epsilon k, and then I need to put two new lm and then del l a m. Fine. Now, I will put this together, epsilon I j k. I put this epsilon here, epsilon k l m, then it is del j del l a m. Okay. So, now I use this relation, epsilon I j k is equivalent to epsilon k I j. So, that I am going to use here, that I am going to use here. So, I will, after that I can write it this epsilon I j k I replace to k I j, because both are same, then epsilon k l m, then del j del l a m as usual. Now, why I write this? Because in both cases, if I write this in a k form, then I can use this famous delta identity, and that is delta I L delta j m minus delta j L delta I m delta this one to the distance 1 I m and delta j L, then delta j delta L a m, whatever is here. Okay. Now, these things I need to be careful. So, when I is equal to L, then it is non-vanishing, and j is equal to m, then it is non-vanishing. So, keeping that, I can write it delta j, L become I. So, it is delta I and then a j, because m equal to j. So, then only it is non-vanishing, minus delta j, because when j is L is equal to j, then it is non-vanishing, then delta L. So, I should write it as delta j, and m I think write is I. Okay. So, this quantity, now if you look carefully, this is, I can write it del I del j and then a j minus, this is double. So, I simply write double J A I. Now, this quantity is very interesting and I can write it, please check it. I am not going to do the elaborate thing here, you can take it as a homework. Then the gradient of this quantity and the ith component is simply this one, okay, and minus this is simply the Laplacian of A and the ith component. So, eventually I prove whatever I wanted to prove, that curl of A, the left hand side, is equivalent to, this is the gradient of the divergence of A minus the Laplacian A. This is the thing I wanted to prove, and very important identity. I want you to please practice this proof, check very carefully whatever is done in today's class and try to do by your own. So, with this note I like to conclude because I do not have much time today. So, thank you for your attention and see you in the next class.